Welcome folks, calculus video. In this case, another video on volumes of solids of revolution. We'll be talking about the technique of cylindrical shells. So we'll start this off with a motivating example. It turns out we'll have an example that's difficult to solve by our existing method, that is washers and discs. We'll develop the idea of a shell, and then we'll see some variations on that shell idea, close with a summary. Okay, so let's think about the region R between the x-axis and the curve x squared minus x cubed. So this curve x squared minus x cubed, a cubic that opens down. If we think about factoring it, we can see it crosses the x-axis at 1 and just touches the x-axis at 0. So here's that cubic, the region between 0, 1, and the x-axis, and we'll rotate this region around the y-axis to obtain a solid. So again, here is our region rotated about the y-axis. If we did what we did before, we would take a slice with thickness dy and try to compute the volume of that little disk, or in this case, a washer, resulting from rotating that slice around the y-axis. So here's our slice, thickness dy, rotate around the y-axis, obtain a disk. The disk is going to look a little bit like this. So for the outer radius, we'll have to solve y equals x squared minus x cubed for x. And for the inner radius, we'll also need to solve y equals x squared minus x cubed for x. As we'll see in a minute, that's going to prove to be really difficult. So again, here's our disk with thickness dy or delta y, rotating around the y-axis, obtain a washer, the washer with thickness dy, and solving for this inner and outer radius is a mess. So if you give this to Wolfram Alpha or something, you can see that one of the branches is this messy quantity 1/3 times all of this stuff. Okay, so we're going to just stop here. Nobody has time to deal with this. There must be a better method. So the better method is to, instead of slicing with thickness dy in this case, since we already have functions in terms of x, is to slice with thickness dx instead. So this is going to give us eventually the cylindrical shell. Now, I remember as a calculus student being super confused about what a cylindrical shell was. I was thinking of a seashell. Instead, you want to think of these cups that you take camping that collapse down on one another with concentric sort of shells inside. Or alternatively, you can think of a roll of toilet paper, right? It's a little bit misleading because the toilet paper goes around and around and around, but you can think of having all of these really, really thin pieces of paper essentially that form a solid. And that's going to end up being our strategy for cylindrical shells. So to illustrate cylindrical shells, in this case, we'll go ahead and think about a slice with thickness dx instead, and rotate that slice around the y-axis. So here's our slice with thickness dx. We're rotating that around the y-axis, and you can imagine that you get something with sort of a circular shape that has just a little bit of thickness. So I'll go ahead and stylize that here. So here's our slice with a little bit of thickness dx. Our slice has some height h. Our slice has some radius r. And you can think about the volume of this slice by getting out your magical mathematical scissors, cutting this slice open, and then finding the volume of the little piece of paper resulting. So the key to this calculation is that the height remains the same, and then rolling out this little piece of paper, we end up with a width that's equal to the circumference of the corresponding circle. In other words, 2 pi r. Of course, this little rectangular piece of paper has a little bit of thickness dx, so we can find the volume dv just by multiplying those quantities together. In this case, that volume dv equals 2 pi times r times h times dx, and here the radius r is given by the distance from the y-axis to the slice, so x, and the height h is given by the distance from the x-axis to the curve, so x squared minus x cubed. This gives us dv is 2 pi x times x squared minus x cubed dx. Just like before, use the definite integral to add up all of these bits of volume on the interval from 0 to 1, and away we go. So that volume V is the integral from 0 to 1 of dV, and again dV 2 pi x times the quantity x squared minus x cubed dx. Fundamental theorem of calculus, away we go, and a slight typo here. Evaluate at 0 and 1, and the volume ends up being 1/10 pi cubic units. Okay, just generalize this to revolving a region R bound between the curve 0, or the x-axis, and the curve f on the interval from A to B, about the y-axis in this case. So again, if we think about a slice, our strategy is going to be to find the volume of that slice and then use the definite integral to add up all of those little bits of volume. So our cylindrical shell with radius r, height h, a little bit of thickness dx. Magical mathematical scissors slice that open to obtain a little piece of paper with width 2 pi r. Again, that's the circumference of the shell, height h, and thickness dx. In this case, the radius is given by r, the height is given by the function. The little bit of volume, therefore, is 2 pi x times f of x dx. Use the definite integral to add up all of these little bits of volume on the interval from 0, or from A to B. So you see our definite integral from A to B of 2 pi x f of x dx. Now this works well in the case where the region is a simple region like this. Of course, there may be some variations on this region, in which case we'll have to calculate the height and the radius of the corresponding shell carefully, but it's always sort of the same idea. So here's an example. Let's find the region R between the y-axis, y equals 1, and the square root of x. You might recognize this region from last time. Find a definite integral representing the volume of the solid created when R is rotated about the y-axis. Okay, so here are our curves. Again, the region in question is the region here between the square root, the line y equals 1, and y equals x. Rotate that around the y-axis to obtain a solid. So we'll think about taking a slice with thickness dx this time, and think about the volume of the shape generated in a shell when we revolve that slice. So again, revolving a slice, we see that that slice, when revolved, gives us a cylindrical shell, height h, radius r, thickness dx. Magical mathematical scissors, slice it open. The volume of that shell is 2 pi r times h times dx. So the challenge here is determining r and h. In this case, again, r comes from the distance from the y-axis to the slice. That's just x. And the height in this case, as it turns out, comes from the quantity generated by the difference in those two curves. So r equals x, h equals 1 minus the square root of x. This gives us an expression for the little bit of volume dv 2 pi x times 1 minus square root of x dx. Now, once again, it's important to have all x's in this quantity because we've taken a slice with thickness dx. Use the definite integral to add up all of those bits of volume on the interval, in this case from 0 to 1, and then just use the fundamental theorem of calculus to evaluate the definite integral. So the integral we obtain is the integral from 0 to 1 of 2 pi x times the quantity 1 minus the square root of x dx. Simplify the integrand, power rule for antiderivatives, apply the fundamental theorem of calculus. I'll leave those details to you. End up with 1/5 pi cubic units. Not surprisingly, just like we did in our last video, where we found the same volume using the method of dis in the y direction. Okay, a couple other variations on the same theme. It may be the case that we revolve a region R around the x-axis, and slicing with thickness delta y will end up giving us a shell, Or we might end up revolving a region R about an axis that's parallel to an X or Y axis. And similarly, we just have to compute the radius and height, in this case of the shell, carefully. So an example illustrating that, let's take the region between the x-axis, the line y equals x to the fourth, and the line x equals 1. Our goal in this case is determine the volume of the solid generated when we revolve around the line x equals 2. So similar to before, we'll go ahead and take a slice with thickness dx, revolve that slice. You can imagine that we get a cylindrical shell. That shell has some radius r, some height h, and some thickness dx. Now the radius r is going to be pretty quick to determine. The height h is going to be pretty quick to determine. The radius r a little more work, and then we'll go ahead and think about adding up just like we did before. So take out your magical mathematical scissors, slice this piece open, and let's find what r and h are. Just like before, the volume of our shell is dv equals 2 pi rh dx. The dx tells us we need all of our functions in terms of x. And here we can see that the height is just given by the curve, so the distance from the x-axis to the curve, x to the fourth. And the radius, as it turns out, is given by the distance from the axis of revolution to the line, or 2 minus x. We can see that the radius is given by this blue distance. Of course, the distance from the y-axis to the axis of revolution is 2. The distance from the y-axis to the cut, and I've sort of put the cut in the wrong place here, so let me fix that. The distance from the y-axis to the cut is x. The desired radius, therefore, is 2 minus x. So we can see this gives us an expression for dv. That expression for dv is dv equals 2 pi times the quantity 2 minus x times x to the fourth power. The volume can be found using the definite integral to add up all of those little bits of volume. Simplify the integrand. Fundamental theorem of calculus, evaluated at 0 and 1, and we see that the volume is 7/15 pi cubic units. Okay, just a quick summary of volumes of solids of revolution. We've seen two main methods here, volume by discs or washers and volume by cylindrical shells. It's a common calculus student error to try to fit a square peg in a round hole. Rather than trying to obtain a disc or washer or a shell, I recommend taking a slice, revolving that slice around an axis, and just seeing what happens. As a rule of thumb, if you slice perpendicular to the axis of revolution, you'll obtain a disc or a washer. And if your slice is parallel to the axis of revolution, you'll obtain a cylindrical shell. So of course, the volume of that disc is pi r squared. The volume of the washer is the difference of the volume of two discs. You can think about it as a disc with another disc punch out. So pi r out squared times the height minus pi r in squared times the height. And then of course the volume of the cylindrical shell is found by using your magical mathematical scissors. You usually end up with something like 2 pi r h dx or 2 pi r h dy. Okay folks, hope you've enjoyed this video on cylindrical shells. Have a great day and we'll see you next time. Bye-bye.